Hi, and welcome to this tutorial where we're going to be looking at importing and exporting with GenFEA and comparing results with other renowned and trusted software. So here we've got AutoCAD open and we've got the stadium roof model that is a 3D line model that you can see there. And this was actually generated in Revit. And we then exported that as a 3D wireframe model. And here in AutoCAD, you can see that those bottom chord magenta elements is on a layer called bot chord, and we've got the rest of the elements on a layer called frame, just frame. So it's not that complex, although there's a lot of elements, but it is going to demonstrate the purpose and how you do this in GenFEA. So the first thing we want to do is set up the base model. So we're going to import a material and we're going to import the sections that we want to map. So we're going to use circular hollow sections. We'll bring in a reasonably large section for that bottom chord, and then a slightly smaller one, also a circular hollow section for the rest of those framing members. We'll keep it simple. We'll just bring in two types here for this exercise. But of course, this can be as complex as you want it to be. Then we go to the design groups. So we're going to go to groups and we're going to create two design groups, one for the bottom chord and another one for the frame element. So we're going to click on add there again and create the group for frames. We'll change the color to cyan just so we can distinguish between them. All right, now let's go and import the DWG. So we're going to click on Import CAD, and we can go straight ahead to where this is located. And if you want to try this, it's in the Revit folder and then under Stadium Roof Model. And just before we open that, let's make sure it's closed in AutoCAD. We'll save it just so we've got the latest version, and then we'll bring that into GenFEA. Right, so now that it's closed, we can open it up here. And when we click on import, we just give it a second to process. There's quite a lot of elements there, and GenFEA does some smart things in the back end. So here we can see now it's converted that into nodes. And if we head over to the framing elements, you'll see that we've got frame elements imported as well. There's a bunch of stuff missing, such as the material, the section. We need to specify those, but you can see the groups have automatically been assigned. That's based on the layer names that we imported. So we didn't really have to create those design groups, but it would create the design groups from the layers automatically, which means we can easily filter these elements. So what I'm doing now is I'm actually creating a filter for the bottom chord. And like I've done with the material there that you just saw, I'm going to click on the first cell, click on the drop down, select the appropriate section, press Ctrl C, and then I'm going to select the cell below it, scroll down, hold in the Shift key, and click the last row and click Fill Range to fill the remaining elements for this filtered group. I'm going to repeat the same process here for the frames. So again, at the top, click the drop down in the section cell, select the correct one, press Ctrl C, select the next row, and then the last row, holding in Shift, and press Fill Range. Now that all of this is done, we should be okay to generate the model. So we can go ahead and maybe close these open palettes that we don't need. And I'm going to right click and choose Update Model. There are some errors because we don't have supports, we don't have load cases. That's fine. I just want to show you that we can import the geometry and it's automatically discretized and brought into GenFEA as a GenFEA structural model. Right, now let's look at importing CSV files. Now for this exercise, we are going to generate some CSV sheets from Dynamo in Revit. So here we've got a portal frame model in Revit, fairly basic. You can see all of those Revit beam and column entities there, but we've also got an analytical model in the background, and that's what we see here when we switch on the analytical model. Now, Revit doesn't produce analytical models anymore like it used to, but we've provided some Dynamo scripts that can do that for you. There's a lot available online in any case, and some shipping with Revit too. Now, if we launch Dynamo, we're going to use the analytical export script. You'll see there's one to generate the analytical model and export it. Both of these are contained within the samples that ship with GenFEA. So if you just pop over to the GenFEA folder in your documents under BIMWERX FEA, then you'll see the samples folder. And within the samples, you've got Dynamo. And there's one for Advanced Steel and another folder for Revit. So it works with Dynamo for Advanced Steel also. And there are the scripts that you can use. Of course, you can adjust those and improve on them if you want. And the sample portal frame model is there too. So if we just have a quick look at the script, it's not complicated at all. We're going to create two sheets from the analytical view. You can change your view there. We're going to create two sheets, nodes.csv, and we're going to create frames.csv. There's a bunch of stuff that happens in the green block, which is the processing, and then it's going to export those data sets to the CSV files. And that's pretty much all we need to do. So we're just going to click on run. It's going to run through, and it pops up with an error or a warning. It's not really an error, it's a warning. And the reason is that I actually had this sheet open while running the script, so I shouldn't have done that. But in any case, it doesn't really matter. It's still going to produce the results that we want to see. So you can just go ahead and do that. And if you don't have any of those sheets open, you shouldn't see any errors. But you can see in the background there in Dynamo, it's actually in the window, it's created that wireframe model, indicating to us that it's done what it's supposed to do. I'm not going to save any changes here. I'll just pop in straight into GenFEA. And then again, we need to set up our base information, such as materials and sections. And then once we've done that, we can go and import that sheet. So what I did there is I clicked on import CSV from the nodes sheet, and then we go to the output folder where that was created. Again, when you import CSV, GenFEA will try and detect what sheet it belongs to, but you can also change that. It's trying to identify that based on the column headers. And we'll do the same for the frames. So we clicked on CSV import there. We just import that and bring it in. Now you can see obviously the material, the section, the angle, and the type is blank, and GenFEA will produce an error if we try to update the model here. So we need to populate some values in there to start with. So all I do is I populate those columns, material, angle, and type. I copy them, and then I select the remaining rows, and I just Control-V to paste it in there. For the sections, we need to work a little bit differently. First, I'm going to assign a uniform section to all the elements just so I can generate the geometry, and then we'll start splitting it based on what they're supposed to be. So now that we've got all of that, let's right-click and choose Update Model. A whole lot of errors because we don't have support. There's a bunch of stuff that is not set up correctly, and also I dragged the column down to fill the rest instead of using the fill range. So it's telling me some of those sections could not be identified. But that's okay, we'll fix it, update again, and that should be a little bit better. But everything now is universal column sections, so we don't necessarily want that. To fix that, I'm going to use the cross select tool, select all of those columns, right click and choose edit properties, and I'm going to set the values. In this case, those are already correct, so that's okay. Let's do the same for the purlins because they're going to be easier to select quickly. So I'm going to activate a side view there. I'm holding in the control button and then selecting multiple regions so that I can add to the selection. And once we've got all of that selected, again, right click, edit properties, and I'm going to change the group there to purlins, and I'm going to change the section there to the cold formed Zs that we used before. And I'm going to change the end releases to torsion pin anyway, or torsion fixed. So now that that's done, I'm going to press escape, and I'm going to right click and choose update model, and we should start to see, based on the groups, the different coloring apply to the elements in the model. Now, we can use the input sheet to filter for the remaining blanks, which will be the rafters. And once we've done that, we can simply go and assign the correct groups of rafters, Control-C, next cell, highlight the rest, and then fill range. And then, of course, we can do the same for the section designation there. And if we remove the filters and select everything again, we can right-click and choose Update Model, and we should have our completed, more updated model there. And if we look at the elements, we can see it's not been discretized as it came from Revit. So we'll right-click and choose Discretize Elements after we clean the nodes. And then if we show the node labels again, we should have an updated model. Now, I'm doing some house cleaning there. I'm cleaning up nodes, renumbering stuff, and fixing the orientation of the beams so they're all uniform across the model. But it's as simple as that. The model is built, and we can see the discretization has happened there based on the element labels being in the center of all the beams. All right, let's have a look at importing from other formats. So of course, you can import from various formats. There are many different ones, but we're going to now use the import from Prokon. So first, let's just have a look at the Prokon model. This is from Prokon's Frame Analysis. So it's a fairly comprehensive model set up here, and we can see what that discretized model looks like in Frame, and it's called wizard.ao3. So let's jump back into GenFEA, and we got to import and import Prokon. So when you import a Prokon file, it's going to create a new project. So you can't add it to your existing project. It'll always create a new project. We won't specify the location in this case because it's not necessary for the purposes of this demonstration, but in a real project, you probably would want to. So we're going to import that frame file. It's going to ask us to map the materials and sections. So we can see there we've got a steel S355JR, so we just need to map it with our relevant material, and we click on the map button. We do the same for the section. So the first one there is a 152 by 152 by 23 H1. So that's the universal column. It's from a different section database than the one that I've got active here in my project. I've got the New Zealand standards or NZ standards here. That's probably from a South African one, I would imagine. But yeah, of course, GenFEA does support multiple section standards. I just haven't set it active on this one, but I could have done that. But you go and map the sections to the desired ones, you click on OK, and it's going to then generate that model after importing it from Prokon. And it will do a lot more than just the geometry. If we switch on the extrusions, we'll be able to see the extruded model shape, and we can do stuff like switch on the supports and view the loads and all of that. Everything is brought across from frame analysis, so it's the comprehensive analytical model that you see within GenFEA. So that's really great because it means that we can use this for testing and verifying and validation, which is what we've done extensively in GenFEA. So we've switched on the supports. I'm just going to increase the symbol size there so we can actually see clearly what's going on. And we can see that that is the exact same model as it came through from Prokon. Great, so we can also export to many formats, one of them being SAP 2000. I'm going to show that in a bit, but first let's have a look at exporting to Prokon. Of course, we can export to DWG, we can export to IFC and a whole lot of other formats, but if we wanted to do verification, we can take our model that we tested here before, the stadium roof, and we can export that one to the Prokon frame file. So we just start up Prokon. Now that the export is completed, we'll fire up frame analysis and we'll see what that looks like. So let's go ahead and open up that exported file. So I placed this one in my documents folder under BIMWERX and projects. So let's go there, and under the Prokon folder, we should see the wizard that was exported, wizard.ao3. The stadium roof, the stadium roof. So there's the stadium roof. We imported it. It takes a little bit of time to open and process, but everything is brought across again. Supports, member properties, materials, loads, end releases, everything is brought across. You should just be able to go straight to analysis, hit analyze or run, and see results. Now let's have a look at member verification and comparison. Now in this one, we've got a concrete model built up out of concrete and steel. So we've got some steel members and we've got a shell element there as well that's already been meshed using GenFEA. And we can export this to SAP 2000. So when we do this, it's going to export a SAP 2000 compatible Excel file. It does it fairly quickly. So once it's done, we can go to SAP 2000, go to import MS Excel spreadsheet. And when we click on OK, oh well, we're just closing the current model. But when we open up that SAP 2000 Excel spreadsheet, it'll take a little bit of time to process, but you'll see at the bottom left there, it's checking the user-defined sections and field names, etc., etc. So when we export to SAP 2000, we actually generate custom section profiles for all the sections exported from GenFEA. This is important because it means it'll always work regardless of whether they are mapped between the two software packages. So we can see once it's imported, 0 errors, 0 warnings, 0 informations, which means everything works. It's really robust. Everything should be 100% accurate. Beam orientations, end releases, supports, loads, material properties, section properties, load combinations, the works. So in fact, if we switch on the model extrusions here, we can see that it visually compares with everything we've got in GenFEA. And if we look at the cross-section properties, for example, and we're looking at the 180 UB 22.2, we can look at those property values that has been calculated by SAP 2000, and we can compare them with that of GenFEA, which does its own calculation. So it doesn't read it from a database. It calculates it using the section library tools within GenFEA, which we cover in other sections. But if we look at the cross-sectional areas there, we can see that they compare. If we look at the moments of inertia in both axes, we can see that they actually compare. They are 100% the same. And if we look at things like the torsion constant, there's a slight variation because of the way it's calculated, I guess, between the two, but within 1% difference between those two. So The cross-section properties, calculations, and comparison results is a good start between the two software packages. And we can do that for all the sections, but we won't do it for the sake of time. But we've already run those comparisons and they're verifiable. So if we run the model, we can see the load case. We only had one in GenFEA, but if we had multiple, they would appear here. All the load cases and load combinations will be brought across. And once we run the analysis in SAP 2000, we can start looking at results and comparing that with GenFEA. So we're switching on the deflection in Z. So we can see there we've got those values, 3.7 something there in the middle. And if we switch on or run the analysis first in GenFEA, it's really quick. So we're just going to run through this, and then we'll switch on the deflection for that same load case, and we can see we've got 3.883 there as our maximum deflection. We see that on the left there from that legend that is displayed, and we can compare that again with here what we've got in SAP 2000, and we've got 3.8253. So really close, very similar. Now if we look at some other results here like the reactions, you can see that they are also very close. So we've got 59.7 there, 5.97 there. And if we look at the results here in GenFEA, very close, also 59.766, etc. So within a percent variation, 1% variation between the two packages, extremely close. And that is for all directions, X, Y, and Z, not just in Z. So it's really good to see that those results actually match, and we can do the same looking across the model and other areas and making sure that the distribution and the calculation is consistently correct across the model, not just in one location. So if you look at those values there and we compare it again with the SAP 2000, we get the same. So next up is looking at the axial forces, and we can see if we look at the axial forces here and we switch on the axial forces here in SAP 2000, we will be seeing similar results, or at least we expect to see similar results. So if we zoom in there a little bit, then we can start to see those values. So 59, 62, 61. We expect that because we saw the reactions, but you can see the exact same values here in GenFEA. Slightly different, of course, but again, as I say, within 1% variation. If we go a little bit further and we look at shear in the first direction here, so we can see 2594, 2588, and if we do the same here in GenFEA, 2562, I can't see what the second one says, 25 something, but very close, very close, right? So that is good to see. Now let's look at the shell elements here. So we've got a value of 1938 there, and if we look at what we've got here in SAP 2000, difficult to read there, but 3290, and if we look at what we've got in GenFEA, very close. So really good to see results that close. And if we look at the shear force in the other direction, we'll just have to zoom in a little bit. It's sometimes a little bit difficult to see on the screen here in SAP 2000. But if we look at that value, 1208.98, so 1208. And if we look here, we've got 1192. It would seem, yeah, 1192. So again, quite close. 1204. And there we've got 1191. There we've got 1251, and we've got 1258 or 1278. Yeah. Okay, so let's move on to torsion. So if we look at the torsion values, again, we're going to see very similar values. So yeah, I'll speed this up a little bit, but if we run through the rest of the checks looking at moments, so currently we're still looking at torsion, so I'm just comparing the results there, and you can see them on the screen. They're very close, they're very similar. If we switch between the two packages, we see virtually the same results. We'll switch to moments now in the one direction, and then we can see the values that we achieved there. Very close. Again, very close. There we go on this side. So we've got 37, 39 there, 43, same as in GenFEA. And if we switch to the last one, moments about Z, we've got 77 there. We've got 78 on the other one. We've got 188 there. We've got similar there. They're very close. So Really good results. We also do NAFEM's benchmarking tests, which is available from the GenFEA website, which is at BIMWERXFEA.com. So BIMWERXFEA.com. And you'll see we've got some NAFEM's benchmark tests done there as well. I hope you found this useful and informative, and give GenFEA a try. Let us know if you have any questions, and thanks for watching. Goodbye.